You know that feeling, right? You get the fresh tree, the box of lights, and you're aiming for that perfectly even spiral.
Oh, yeah.
But you always stand back, and it's just, bunched up in one spot and way too stretched out in another. It just never looks quite right.
Well, what you're running into there is a classic problem. It's the human estimation versus the cold, hard perfection of geometry.
And that's exactly what we're doing in this deep dive. We're looking at the math behind that perfect spiral.
Mm-hmm.
How do you model it? And maybe more importantly, how do you figure out exactly how many lights you need?
It's geometry hidden in plain sight. And the model we're looking at, it really boils down to three key things about your tree. You need h, the height.
Okay.
R, which is the radius of the base, so how wide it is at the bottom.
Right.
And n, which is just the number of times you want the lights to wrap around the tree.
Okay, so let's unpack this a bit. We have to map this path in 3 dimensions. So you've got these coordinate equations for x and y. But x and y usually make a circle, right? How do you get it to spiral and shrink at the same time?
That's the elegant part. The equations are built to do both things at once. First, you have the rotation.
Spinning part.
Exactly. That comes from the cosine and sine functions. You'll see a term in there with 2 pangs h. That's what's driving the circular motion. And it's tied directly to z, your height.
So the higher you go up the tree, the more it turns.
Precisely. It guarantees you complete exactly n turns by the time you hit the top.
And the second part must be what gives it that classic cone shape, the taper.
That's it. You look for the term that looks like hz, h times r. That's really the magic scaling factor here.
Okay, walk me through that.
Well, think of z as your position. It's 0 at the bottom and h at the very top. So as z gets bigger, hz gets smaller.
Right. The numerator shrinks.
It shrinks. So that whole fraction just smoothly reduces the radius from its full size r all the way down to 0. That's your perfect cone.
So now we know the exact 3D path. But here's the real question for you, the listener. You know the path, but how much wire do you actually buy? A straight line is easy, but this thing is twisting and turning in space.
And this is where things get, well, a lot more complicated than people think. Calculating that length, the arc length, is not simple geometry. You're summing up an infinite number of tiny little segments along a constantly changing curve.
Which is why the formula for, the total length is so intimidating when you first see it.
It is.
And here's where it gets really interesting for me. This isn't high school math. You need calculus, right? An integral to sum all those little pieces. And I'm looking at this formula, and there's a function in there that looks pretty out there.
The sin, that's the one.
Yeah, that's the inverse hyperbolic sine function. And its appearance there really shows you how advanced this calculation is. You need what are called transcendental functions to solve this.
So you need transcendental functions just to string your Christmas lights perfectly.
If you want it mathematically perfect, yes. It's high-level math sitting right there in your living room. And, the fact that a simple decorating problem can demand that kind of computational power, it really speaks to the hidden complexity in our world. That kind of automation and calculation is exactly why specialized tools are so vital. And this deep dive is sponsored by Embersilk. If you need help with advanced AI training, software development, or even just figuring out where intelligent agents could make an impact for your business, you should check out embersilk.com for all your AI needs.
So what this model really shows us, I think, is that a simple act of holiday decorating is it's governed by some really elegant and rigorous mathematics. It's this beautiful link between the practical world and pure geometry.
So what does this all mean then? For me, it means that even the most joyful, sort of whimsical parts of life have this knowable, beautiful structure underneath. And knowing we can model that we can solve it, should make you really optimistic about what else we can figure out.
And it raises a fascinating question, doesn't it? We've just modeled a perfect conical spiral, but nature is full of spirals. Think about a nautilus shell or the arms of a galaxy.
Oh, right. Those aren't cones.
They aren't. They're often logarithmic spirals where the radius changes exponentially, not linearly. So you can start to think what small change to these equations would transform our Christmas tree into a galaxy.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.